Mohammadi, né, que é professora atualmente da Universidade Federal de Pernambuco. A professora, ela é conhecida do Departamento de Física, da Unidade Acadêmica de Física da UFCG, e por um tempo de pós-doutorado que ela passou em 2017. A Azadeh possui graduação pela Universidade Shahid Beheshti, e eu não sei como é que pronuncia direito isso.
Tá ok.
Mestrado em Física de Alta Energia pela Universidade Mazandaran e doutorado também em Física de Altas Energias pela mesma Universidade da Graduação. Depois disso, ela veio para o Brasil e fez um pós-doutorado na Universidade Federal da Paraíba, em João Pessoa. Passou por aqui, né, foi para Campina Grande, em 2017, e depois foi para a Federal de Pernambuco, onde se concursou lá em 2018, se não me engano. Bem-vinda, Azadeh.
Obrigada. So I'm sorry, I will change to English because I didn't prepare in Portuguese. So thank you, Douglas, for the invitation, and this is always a great pleasure to see people from UFCG, and I had really good time there. Okay, so today the talk is about kink collisions. Okay, and first I will introduce briefly what is a kink and what is a kink solution. Then I divided the presentation to two parts. The first one is the kink collision and studying the effect of quasi-normal modes and comparing with normal modes, studying this effect in bound and scattering states, in the kink excitations, and finally in the kink's collisions. And then I will explain it is known that after the collision appears some fractal structure that I will show that with quasi-normal modes, this is gradually disappearing. Then I will talk about another work. These two works, they are the works I did with my PhD student, João. The second one is about the kinks, but different types of kinks they are called long-range kinks. They have long-range tail, which means that normal kinks, they are exponentially decaying. I mean, exponentially fast, they go to the limits, but the long-range ones, they are power loss. So it takes a long time you get to the boundaries, which means that if you have two different kinks or kink anti-kink, they will see each other for a long range. So they are highly interactive. This is really open question. Actually, there were a lot of papers. Then since last year, there appeared some papers proving them wrong, that the supposition was wrong, the way people were starting to study the collision of these kind of kinks, because people were doing simply the way they were doing with the exponentially decaying kinks, the normal kinks people knew. But then people proved that, and this was strange because the result was strange because, like, for example, for kink and anti-kink, it is known that they attract each other, and kink they repel. But in the case of kink anti-kink for long-range tail, people proved that they repel, which was really strange behavior. No one was expecting that because they behave like particle anti-particle. So people were expecting a kind of attractive force between them. So then people started thinking maybe there is some supposition here is wrong. Then people showed that the way people measure the force and they start the collision is wrong. So in this sense, I wrote in the abstract that it is invalidating many results existing since last year. And because of this reason, we became interested. So we did work in this line, and actually, it's really recent work. We put it in archive like 2 weeks ago. So any comment, any suggestion is appreciated because still is not published. Okay, so first of all, what is a kink and what is anti-kink that I talked about? kink is the solution appears in 1 + 1 dimension. It's a topological solution. Then I will show that in what sense it is topological. Then the simplest case is you have one real scalar field. So you have Lagrangian for one scalar field in 1 + 1 dimension. The simplest and the most known theory is phi-4 theory, which is the shape of it. It is the way I showed here. Even I have the graph of it. Then you can see that there are two minima. These minima, obviously, they are the normal minima that just by looking at the potential, you see they are minima of the potential. But then you can prove that there can be other types of solutions that interpolating between these two minima, and they are vacuum solutions. But the energy of this vacuum is higher than these ones that you see trivially. Looking at the graph, they are called trivial minima. In the sense they are trivial in the sense that they are not position dependent. Okay, they are just at one specific. It has one specific value. Okay, but the other solutions that we call them kink solutions, they are the ones interpolating between these two. They have this shape that I showed here. This is for lambda phi-4, but all of them, they have similar shape. Then, okay, so here you have the Euler-Lagrange equation. Solution of it gives this tangent hyper, which is x dependent, obviously. Okay, so it is going from one minimum to another. Okay, it's interpolating between these two. Then there appears a question: if this vacuum has higher energy, what protects the system not to decay to the lower energy? Because we know that if you have the possibility for the system to have lower energy, the system will decay. This is the minimum energy principle in physics. But there should be something to protect this kind of solutions. Then I will show that they are topologically protected. So you can associate kind of topological charge or winding number to them that then you in the context of it means that topological in the sense just in 1 + 1 is easier to see. Then the result of it, you can define a charge which is dependent on the value of the field just at infinities. So you can change the geometry the way you like. So you can distort it the way you like. If you keep the infinities the same, then it will have the same topological charge, so they are equivalent. Okay. So then these kind of solutions are interesting. Actually, this is a known, historically known in 19th century. People found it in water, this kind of waves. Then these waves, they were like traveling without changing the shape. Okay, and then strictly speaking, a soliton is the one has localized energy density, and it keeps it while moving, so it can have just up to a phase shift, and after the collision it keeps the shape. This is more strict, it is stricter limitation, because we know a lot of solitons that they keep the shape. This is due to the interplay between the nonlinearity and dispersion, because normal wave, because of the dispersion, will disappear. But if you have nonlinearity compensating the dispersion, then it can keep the shape. But there are many of them that after the collision, they disappear. The difference between them, we call them, when after the collision, they keep the shape, we call them integrable. Okay, they are integrable. The system is integrable system. But the ones that they don't keep the shape after the collision, they are called non-integrable. We are in this work in these two works I'm presenting, we are more interested in the non-integrable ones, because they are much richer in the phenomenon appearing after the collision. Because for integrable kinks, the integrable system that after the collision they keep the shape. One example is Sine-Gordon kink. It is that After with the collision, they just pass through each other without any change, okay? But this is not true, for example, for this lambda 5-4 that I showed. So we call them solitary wave. Some people call it soliton too. Actually, it's common in literature, but it doesn't have that strict condition of after the collision keeping the shape. So I'm more interested in the collision of these these solitons of non-integrable system. Okay, so here you can see that the energy density is localized. In this sense, they behave like a particle, okay, because of being localized in space, okay. Because of that, we call them soliton, because we add this on at the end of the word, like neutron, electron. Here, soliton, because they behave like a particle, at least before the collision. Then there is mass of the soliton, which is simply if you integrate the energy density over the space, you get the soliton mass. Okay, then I said that what protects the system against decay is the topology you associate. Okay, you can define the vacuum manifold, and it should be topologically distinct. But I don't go through this subject more, because okay, it needs more. I think it's not that important. Here, what is important is we can associate to this system a topological charge. Here, it's a topological current, but it doesn't mean anything, this current, because it's not coming from the continuous symmetry, and it's not related to Noether's theorem. It's kind of reversed, because spontaneous symmetry breaking is creating this current, or zero component of it is the charge. And then you can see that the charge is related to the value of the field at infinities, okay? So in this sense, it's topological. So if Q is the topological charge is 0, you have non-topological soliton, even if you have some configuration in space that it is non-trivial. It means that it is X-dependent. It will decay to the trivial solution, okay? Because okay, the energy is lower, so of course there is no topologically is not protected. So if you want to protect it somehow, you should put a conserved charge there to protect it. For example, sometimes people do with non-topological solitons, they put a charge, electric charge there. Then we know electric charge is conserved, so this is protecting the system against decaying. Okay. So then why is it this is important? In 1+1 you have kink. 1+1 is not it's not the space-time we live in. So why does it matter? Actually, because of the symmetries of the system, sometimes you can in practice treat the system lower dimensional. For example, it can be 2+1 or 1+1 system. I will give one specific example here that exactly this kink behavior appears. For example, consider a material. It's a polymer called polyacetylene. Polyacetylene has parallel chain of atoms. Then the electrons in the same chain can move around, but they can't hop to the other parallel chains. So in practice, the system is one-dimensional, okay? Then interestingly, because of the many reasons, the system is not really static, because electron doesn't stay in the same place if you have like the effect of temperature, or you have zero motion, 0 point motion, so the system doesn't stay the same, so starts oscillating. But interestingly, in this system, it doesn't oscillate around the atom site. It moves slightly. Okay, the distance between these atoms is around 1 angstrom. Then it's funny that the system first goes to the right or to the left around 0.04 angstrom, then start oscillating around this point. And it doesn't matter left or right because the system has parity symmetry. So randomly, it is oscillating around the point in the right or in the left that I showed as A and B, okay? So you can show this displacement as a field, okay? You can define it in the regions they meet, like the region that the electrons, they go first to the right, then oscillate, and the region electron goes to the left and then oscillates. The transition between them creates kind of kink. So then you can define a scalar field the way you have like for a kink, that it is interpolating from one vacuum, vacuum A, and vacuum B, because one side of it is the electrons moving to the right and oscillating, another one to the left and oscillating. Then you can show the potential exactly like the way I showed for lambda phi 4. So you can see that in a real system, they can appear because of the symmetries of the system, because if just the electrons can move in one direction and can't hop between the different layers of atoms. So in practice, we are working with one plus one dimension. The plus one doesn't matter because even the Kink solution that we showed for lambda phi 4 is static. So the space part just matters, just one dimensional, the spatial part. Okay. Then there is another important thing in this context that worth mentioning is the BPS condition or self-duality condition, which is if you have a first-order equation that solves your second-order Euler-Lagrange equation, this is called the BPS condition, okay? Then, okay, I can write the potential. This is always possible in 1 plus 1, okay? I can write the potential in the form of 1/2 of W phi squared. W phi means dW d phi squared here. This W comes from the context of supersymmetry, okay? But here, it doesn't matter. For us, it's just another potential-like thing we are defining. We call it a superpotential, because it comes from supersymmetry. Then you can show that you can write the energy as I wrote in equation 2. So it's just playing, completing the square. You can write it this way. Then you can show that this Q part of the energy is the minimum of the energy, because obviously the first part is squared, so it's non-negative. So it just adds to Q, okay? So this defines the minimum of energy. Because of that, the BPS solutions are really important because they are minimum energy of the system, so they are stable, okay? And besides that, the energy of the system, you can show that it's related to Q, which is the topological charge of the system. So somehow the topology defines this minimum energy, okay? Okay, this is what I wanted to talk about the subject of what is a kink and what is a kink solution and what is relevant here, okay? Then this is, I want to start the first part. This is one of the works I did with my PhD student, João. It is, it deals with the system that has quasi-normal mode. First of all, what is a quasi-normal mode? Quasi-normal mode is the mode that the frequency or the energy, depending on the units you are working with, is complex number, okay? So the Hamiltonian is not, if you are you can work with it classically or quantum mechanically, but if you look at it quantum mechanically, it means that the Hamiltonian is not Hermitian. The system decays, so it's not normalizable, but they are not rare in nature. For example, you can explain radioactivity with these kind of modes, okay? Because radioactive nucleus is not completely stable, right? Because the particle can tunnel at some point. So you can explain the system with quasi-normal modes. And they are really, really important for example, for recently we know about the merging of the black holes. If you with this measurement, you are with the quasi-normal mode measurement, you are able to measure the mass of the black holes merging. Okay, for example, and they are purely outgoing waves. Okay, which means that, okay, if you have a system, the system just leaks energy. Okay, which is, if you write the frequency or energy as a real part plus imaginary part, the real part is responsible for the oscillation, like a normal mode. The imaginary part is responsible for the decay. So I was curious to see, because there are really low number of papers in the literature looking at the soliton collision with, actually I don't know more than 1-2 papers that they are dealing with these quasi-normal modes, okay, for the Kink collisions in this context. Then I thought, okay, let us build a toy model, a really simple model, because I knew that quasi-normal modes are really difficult to find. Numerically, many methods we know they are exponentially diverging in the error, so it's really difficult to find them. Even if you have some quasi-normal modes that the modes are close to each other, it's really difficult to distinguish between them numerically, because many systems we know you should solve the system. It's really complex, so you should solve the system numerically. Then I thought, what can I do to make the system analytical? Okay, so to be possible to solve it analytically. Then I thought, okay, the simplest case I can consider is that if I have a square well potential, and then changing the square well potential, imagine you have in this square well potential, you find the normal modes. This is a simple quantum mechanical system. You know how to solve it. Then if you make the system to behave like part of this, besides this square well, you have two, if I put two barriers, then any normal mode that stays above this barrier, but look at the one in the left for square well potential, any normal mode here in the left, then because of having this barrier, it starts leaking. So in practice, I will be able to create a system, a simple quantum mechanical system that has quasi-normal modes. It's purely outgoing. It just leaks energy. So this way, I can find many things analytically, because, okay, quantum mechanically it is known system. Then, okay, but there was one difficulty. I should define this. I want to see this quasi-normal mode in the Kink collision or in Kink excitations. So what is the relation between this and the Kink? So what I thought was, let's start with, imagine you have a Kink solution. I don't know what is the shape, okay? You have this phi k. Then in equation 5, you can do the stability, you can do a small perturbation and write the linear stability equation. Then what appears, it looks like Schrodinger equation with the energy here that is omega squared, okay? Then this potential here, if I make this potential to have the shape I showed here, then I find accordingly the Kink solution for the original potential in 1 + 1 dimension, this V of phi. If I find a soliton or a Kink here with this V of phi, and then the second derivative of it gives this stability potential, then I will be able to create quasi-normal modes for the Kink excitations and for the Kink collision, right? So this way, so here you can see that if delta gamma goes to 0, delta L going to infinity, I will get the square well potential, right? So I can encode the information about the quasi-normal mode with these two parameters. Okay, so to have this I formulate this stability potential, this square well potential, and the one with two barriers, okay, with the symmetry of x to minus x. So obviously in equation 7, if I put delta gamma going to 0, I will recover the equation 6, which is the square well potential. So what could be the potential, the original potential in the Lagrangian that gives this stability potential that I showed in the figure? Then the simplest case was, if the potential is second order in scalar field, then the result of it will be a number, right? It will be independent of phi when you do the second derivative. So this was the simplest thing we could do. Then just I need to find the soliton solution here. So equation 8 is the corresponding potential in the Lagrangian for the square well potential, and equation 9 for the one with two barriers. Then, of course, I need to impose the continuity equation in the potentials, okay? I do with the first derivative and second, I do with the potential and first derivative of it to be continuous. Besides that, I impose BPS condition. I want the stability of the system to be guaranteed also. With these three conditions, I recover the translational symmetry of the system. So related to this translational symmetry, of course, there is one zero mode, okay? It is always true. Any continuous symmetry of the system, you can associate a zero mode, okay? Which means that translational symmetry, it means that if I move the kink from minus infinity to plus infinity, any point, it doesn't matter, it's degenerate, okay? So it doesn't cost energy, okay? So then the potential we designed has this shape. Then you can see that it looks good, although I really manufactured everything. Everything seems really highly toy model and really cut pasting the pieces, but it looks good because it has exactly the two minima that is needed, because for having a kink you need at least two minima. So this really looks like phi 4, okay? And the soliton of it looks like phi 4 too. It's not tangent hyper, but it is similar, okay? So with the condition I put for the potential and the derivative of the potential to be continuous, I can here I guarantee that the phi, the scalar field phi, is continuous up to second order in the derivative. Okay, so then it's easy. The square well potential, we know how to find the eigenmodes. We know how to find the bound states. These 11 and 12, they are transcendental equations. They are implicit equations for the eigenmodes. And of course, there can be more than one. For even and odd eigenfunctions, I just put here the eigenfunctions also, but it doesn't matter. So the eigenmodes are coming from these equation 11 or 12. We worked with even eigenfunction, but it really doesn't matter. You could work with the odd one. So here we looked at the bound states of the square well. This was the original plan, right? To look at the bound states or normal modes of the square well potential. Then seeing that if you put it in the the square well potential with two barriers, what happens? In this case, it turns to scattering modes, right? Because it leaks, so it will be scattering. It's not bound mode anymore. So for the square potential with barriers, I'm interested in the scattering solutions, okay? Which is then responsible for the quasi-normal modes. So this is just separating for different regions and define what are the parameters of the system. Then, okay, you can, based on this, obviously, if you impose the continuity equation, you can find the F1, F2, G1, G2, and the rest of the parameters here. I didn't put the result because it really doesn't matter. So knowing this analytically, we could find the transmission and reflection coefficients analytically, okay? Then this is the result. Okay, there is one more thing here, let me say. As I said, for quasi-normal modes, we know that it is purely outgoing. If it is purely outgoing for the quasi-normal modes, I should impose F1 equals 0, because it should be just outgoing. So with imposing F1 equals 0, I can find the result for quasi-normal mode. Here, I'm showing the transmission and reflection coefficients for quasi-normal modes. It is a known fact that if you have quasi-normal mode, in the transmission coefficient, you will have a resonance around that mode, okay, around the oscillational, the quasi-normal oscillational mode, okay. Then we wanted to observe this, okay, for the quasi-normal mode. So what we did was, here you can see that from down to top, we are changing the width of the square well potential, but this is just changing the original square well potential. But what is more interesting is from right to left, we are changing delta gamma. Delta gamma, as you remember, encodes the information about the leak of the energy. So for really small delta gamma, the system still didn't start leaking because the mode we chose is below this barrier. So still the system behaves as a bound state. So you don't see any resonance. But when you increase delta gamma, the resonance appears around this quasi-normal oscillational mode, okay? And as you increase delta gamma, you see that it gets more localized around it, which means that if you, for exciting this mode, you need much more fine-tuning, because it just excites and gets almost transparent. This is the interesting part. Imagine you have an incident wave. If you fine-tune the incident wave really close to this mode, excites the mode with really high probability, okay, which is normal. Here, just to see why delta gamma large gives this, which is highly non-trivial, because unfortunately, the number of the degrees of the freedom we have with how we can control the parameters in the system, for the square well potential, after this imposing continuity equation, the BPS condition, and scaling all the parameters to be dimensionless, remains just one controlling parameter for the square well potential, and remains 3 of them for the square well potential with 2 barriers, okay? So then you can see that if I fix the width of the square well, and if I fix the gamma that it is fixed here, then delta gamma and delta L will be they are not independent, okay, unfortunately, because as I said, when delta gamma goes to 0 and delta L goes to infinity, you could recover the square well potential, but as you see, they are not independent, okay. But there is one good point. From the slope of this graph, you can see that for small delta gamma effect is more dominant, and for delta gamma above 2 point something, the effect of delta L is dominant, okay? So when you look at this graph, for delta gamma equals 3, it means delta L is increasing, and when delta L is increasing, it is getting closer to a square well potential. So it needs a much more fine-tuning for exciting this state, because for the normal mode, it is exactly that point. So when you get close to that, it's really narrow window you have, okay? So then we looked at, okay, we imposed this outgoing boundary condition, and we looked at the frequency of the quasi-normal mode, the oscillational part that is capital omega, and the gamma is the responsible for exponential decay. Then here you can see that for delta gamma close to 0 or small delta gamma, still the system didn't start leaking. It didn't go to quasi-normal mode, so the decay is 0. But at some point, when you increase delta gamma, then the normal mode changes to quasi-normal mode because it has the chance to leak. So with delta gamma, then the decay starts increasing. But then after, as I said, above 2 point something, the effect of delta L dominates when delta gamma increases because they are not independent. So when delta L increases, it means we are getting close again to the square well potential, so it decays less, obviously, because for square well potential, there is no decay. Then you can look at the oscillational mode, the oscillational frequency. Then you can show that below this value, okay, for small value of delta gamma, the frequency because of the height of the potential is changing. The frequency is reducing. And you can show that it is just purely bound state. Okay, as I said, it starts leaking after specific delta gamma. Then after that, exactly at the point that there is a dashed line, after that it turns to quasi-normal mode. So as delta gamma increases, delta L is increasing. So if delta L increases, we are getting close again to the frequency of the normal mode of the square well potential, which is shown in the straight line without slope that I showed. This dotted line is exactly the border between the bound and quasi-normal modes. Then it's really easy how to find it. You can see how to find it. I will get back to these scattering solutions. This M factor here, if it's real, it is it's oscillatory, so it is scattering mode. But if you put M as imaginary value, then it will be decaying. So then you can when M is imaginary, you recover the bound state. So to have these two together on the threshold, M should be 0, right? Because M at the same time can't be real and imaginary. So it should be 0. If you put M equals 0, then you find this dashed line, the dashed line I put in this figure. We put in this figure. Okay, now let's, as I promised, let's get to, actually I spent a long time there. Let's get to the collision. So the most known unsoughts for starting a collision is additive unsought. Simply you put together one kink and one anti-kink with specific velocity and then start colliding them. In this case, it is known that for the one I'm saying in the beginning, there is no quasi-normal mode. It's a normal mode, okay? You can prove that there are 3 scenarios. They can simply create buy-in and then start radiating. Buy-in, I mean a combination of kink, anti-kink, and then gradually radiating and decaying. So one of them is just annihilation. The B figure, the figure with index B, here there is a, let's get back to this B because it's more tricky. C1 is, another scenario is they just simply collide and reflect. And then, okay, because of having enough energy, they can start oscillating, because we know that if you find the normal modes are bound modes. Bound modes means that the oscillations, they will be bound to each kink or anti-kink. So it will be excited, this oscillational mode or vibrational mode, or even called shape mode. They will be localized on the kink, anti-kink. So you can see that they reflect. Besides a little bit radiating, it can have this oscillation excited. But there can be another scenario that is creating a buy-in in the middle, colliding a couple of times. So like you have kink anti-kink joining because they really like to attract each other, then having enough energy to separate because there is initial kinetic energy, then there is a mechanism called Campbell energy exchange mechanism, that the kinetic energy in the beginning could transfer to this vibrational mode, to this normal mode of each kink, store energy there, and then, okay, of course they want to be together, but if they have that much energy, then the system can recover the kinetic energy, and then they reflect again. Okay, then you can show that this is called, this scenario B is called resonance window that you have in the middle. Okay, that it is after a couple of times bouncing, the system separates, the kinks reflect, they reflect. Then it is proven that a below specific velocity, it is, I mean, the initial velocity of the kinks colliding, it is always annihilation. It's scenario A. If it is above a specific velocity, they will just reflect. But if you have intermediate velocity, and if the condition is right, you have specific velocities, you can have this scenario of resonance, this resonance windows you have. What I said about the Campbell exchange energy mechanism, then now people know that the scenario is a little bit more complicated than what Campbell said. It's not just, the only possibility is not the vibrational mode or shape mode of each kink. Even the buy-in, the mixture of kink and anti-kink can store the energy if there is a chance to have a bound state of the pair. So now people know more about this mechanism. So this graphs I'm showing, it's for our toy model. So it's behaving exactly like 5-4 model, which is really strange. We were not expecting to see. Actually, up to the point we checked, everything matches with 5-4, although it's highly manufactured, this model. Then this is a graph of final velocity as a function of initial velocity. Then you can show that this is called the resonance windows. Then interestingly, you can see that below specific initial velocity, final velocity is 0, which means they annihilated. And above specific velocity, which is called critical velocity, they just reflect. But in the middle, there is this resonance windows, which means that depending on the initial velocity, they can reflect after some bouncing, or they could just simply annihilate. And this behavior, then we proved that, I mean, the first time for 5-4, it is proven many years ago that it has fractal structure. And it is true even for this model that we are considering as a toy model here. Then you can see that, okay, each window you look for 2 bounce windows, for each window, when you increase the velocity, each time it increases, we are looking at the center of this kink anti-kink field, the mixture, okay? We are just looking at x equals 0. So with these 2 bounces, for each window, when you increase the window number, the number of the oscillations in the middle is increasing, okay? Then people formulated in the formula I showed here, and this omega appearing here is exactly that oscillation frequency for it's related to that shape mode or vibrational mode, which is interestingly the case for this model also. And this is interesting to think about. Each time when we, from one window to another, we are moving, we are increasing the initial velocity, right? Because you can see it in the left graph. So as you increase the initial velocity, the system has a higher kinetic energy, so it gets more difficult to join again and bounce again. It takes longer. Then you see here after 10 times, after this window number 10 that we put the last one, then it's not possible. Then the initial velocity is that high that can't create this bound state. So they simply reflect. So then we show that we introduced another parameter here, epsilon, which is related to, we encoded the delta gamma and delta L effect, the effect that I showed in those potential barriers in epsilon. So when you increase epsilon from 0, you go gradually go from normal mode to quasi-normal mode. Then you can see that with quasi-normal mode, the number of the resonance windows is decreasing, okay? And the critical velocity that after that it is just reflection is increasing, which makes sense because the system is leaking energy. So bouncing gets more difficult, okay? And besides that, the system needs much higher initial energy or velocity to be able then to just simply reflect. Then interestingly, we looked at the fractal structure. We looked at these resonance windows in smaller and smaller scale to see if there is really fractal structure. Because if we do like the first 3 graphs we showed here on top, 1, 2, and 3, this is for epsilon equals 0, which is just with normal mode. You can see that as much as I zoom in, this box that I put here, as much as we zoom in here, you see that appears more and more modes. Then people showed for lambda phi 4, for example, that next to the 2 bounce window, there is 3 bounce window. Next to 3 bounce window, there is 4 bounce window. And this is, as much as you look more and more closely, appears infinite times, which is exactly what you expect from fractal structure. Fractal structure, you can just simply think about cauliflower or something that repeats itself in small scale and large scale. They look the same. And if you look here, we zoom in and we see that they look alike. But then we did more carefully with the definition of the fractal. We measured exactly the fractal dimension. Okay, and these red ones, the graph below, it's with quasi-normal mode. Then when we zoom in, at first it looks like it is repeating, but then if you zoom more and more, you see that it gets completely desertish, so it loses the fractal structure. Then we formulated it with the fractal dimension, and we saw that yes, it is. If you zoom in, you see that it loses the dimension of this fractal dimension. I don't go through this because I don't have enough time to do that. You see that the slope doesn't stay fixed so it is not, when we look in smaller and smaller scale, we don't see the same dimension for the quasi-normal mode. And we see that as much as we look closer, it gets closer to dimension 1, which is aligned, which is expected. Okay, when you don't have fractal structure, the dimension is 1. So in the case of normal mode, we showed that it is, I have it in this table, that it is around 0.84 to 86, okay, which is a fractal dimension, and it keeps it when you go in smaller and smaller scale, but below it is for quasi-normal mode, and gradually you see that it's getting closer and closer to 1, which is the normal dimension for a line, which means that it is losing fractal structure or self-similarity. We did another test that I'm not going to talk about it here for the self-similarity. So we showed that it is the resonance windows are closing with these quasi-normal modes, and the critical velocity is increasing, the fractal structure is lost. But you can see that this is a really gradual process. So as much as you turn on more as much as the barrier gets deeper or thinner, we get closer to, we get more this effect. It loses more the self-similarity and increasing the critical velocity. Okay, another work I wanted to talk about, it's again about Kink's collisions. This is what is, I said that there appeared correct way of looking at the system. really recently, last year appeared. It has been appearing because still people are discovering how to treat the system. So we started looking at the specific class of models. We looked at this equation 19 with this class of models, specifically when n is equal to 2 and 3, which gives phi 8, phi 12. For 1 plus 1, you should be careful. When you work with higher dimensions, dimension matters, because if the scalar field it has dimension, then at some point it stops being renormalizable. But in 1 plus 1 dimension, the scalar field simply doesn't have dimension. So you can increase the power of phi as much as you want. So what we did was, okay, considering this class of models, then we found we imposed the BPS condition. We found the implicit equation for the kinks for phi 8 and phi 12. Then this is equation 24, shows the mass of each kink. Here, this is the interesting part. For phi 8 is the blue line, and for phi 12 is the yellow or orange line. You can see that around the minimum, it's more flat, which is not the case for phi 4. For phi 4, the second derivative of the potential at minima is non-zero. But for these models, when we call them long range, the second derivative is 0. In this case, for phi 8, it starts from a fourth derivative to be non-zero, and for phi 12 starts from a sixth order in phi. So because of that, and then you can see that, I will show it here. If you look at the tail of these kinks, you see that they are power law. It's not exponential as in the case of phi 4 or sine Gordon or the known ones that people work with, which is exactly the difficulty, because it means that the system is really long range. So the kink and anti-kink, they will see each other for a long range. So it's highly interactive. So this was the problem, because then I will show that what people were doing and what was wrong about it. So there appeared one nice method by Milton last year that, okay, he thought that, okay, what can we do? Because there is a problem. We can't just simply put together two kinks like these additive ansatz that I showed. So what do? We just join this kink and anti-kink and consider just the kink part. Okay, we look at the kink part. It doesn't matter. This force is created for the kink to move around, to accelerate. Is created by whom? It doesn't matter. Okay, so we will have an accelerated kink with this equation below equation 27. So this was the ansatz. And then rewriting the equation of motion in the form of equation 28. Okay, and then here there are two things. The A dot, we suppose A dot squared is small because we are considering slowly moving kinks. So we are in the regime of non-relativistic, which is not really bad because kinks are highly massive. So in this regime, mostly they are in this regime. Besides that, they are accelerating slowly, okay? And because of that, because of accelerating slowly, I could still use the BPS equation here below equation 28, because the BPS equation is a static equation. So you can't just simply use it. Here you can use it because it's slowly moving everything or slowly accelerating. So we define this acceleration A. We define it with this second derivative of this capital A, okay, because this is acceleration, this is second derivative. It has to do with the position, so the second derivative gives the acceleration. We define it with minus because we know that kink and anti-kink in principle should the force between them should be attractive. I'm sorry, I think I'm passing the time, but I will try to be fast. In 5 minutes, I will finish everything. Okay, so in this case, using this first order equation for eta, okay, we could just simply look at this eta prime, the equation 29, and solve it. This is our, but this is not possible to solve it analytically, so you can just simply solve it numerically, okay? Then you have the option of doing the simulation and see if this whole approximation and these unsought match with the collision in the numerical result or not, because they should match. And then we do some extra approximation just to have analytical result, okay? So we look at just the tail of the kink in the left, because this is the long range, the tail that meets the anti-kink, okay? Then in this approximation, the whole approximation Milton did is that the other tail doesn't matter. The tail facing, the two tails are facing are the important ones. So we do all the approximation we do around this tail, and we find the acceleration, which has this for phi 8 and for phi 12, this has this position to the power of 4 shape. Then if you do, interestingly, if you do with like Noether theorem and these methods, if you do, always you get this power 4 for phi 8 and for phi 12, it's trickier. I mean, the ones that they have quartic shape around the minimum of the potential, you always find this to the power of 4, and the other one, it is power 6, I mean, around the minimum. So it always appears with this power 3 in the force. Then, okay, but I didn't say what is this delta A, then you need to approximate everything to find what is this delta A, but I'm not going through these details, but they are important details, just I don't have time. So now, knowing this, so we know that first order equation coming from Milton's equation, then some more approximations that give some analytical results. And now let's do the collision. Then people prove that the simple additive unsoughts doesn't work. It is because then you can show that when the kinks are showing or are seeing each other for a really long range, so then it doesn't follow really the equation of motion. So it's that bad that creates some radiation, it creates some pressure in the middle, and instead of attraction, this pressure creates some repulsion. That is, it was really weird result, but then now people know that you should start the system with really different unsoughts. That here, the suggestion was to put Heaviside function, this theta is Heaviside function. So simply putting kink in one side, anti-kink another side, and not caring about the effect of one in the other, okay, just joining them. Then, okay, if you do this way, you get these two shapes. Around 0, it gets this cusp, so the derivative won't be continuous. So to make the derivative continuous, then you can use the least square minimization, which is each term here is 0. So you're just guaranteeing that the equation of motion is satisfied, the kink is at position A, and anti-kink is at position minus A. So if you do that, you see that it's smoothened out, this cusp that you see around 0, okay? Then, okay, then we did the collision, we found this result. This result actually became really interesting because in the scenarios of the kinks with exponential decaying tails and the ones that they have long range tail, just one side, always create buoyant, and then they can radiate away, they can annihilate. But with these kinks that they are long range from both tails, from both sides, you see that there is no buoyant formation, which is it has never been reported in literature, okay? So this was really interesting result for us. Then this blue line is the one with the first order that comes from the Milton method, that you see that it really matches well the collision here. So it's really nice method, but it's nicer for phi 8 than phi 12, because then people know that as much as it gets more long range, then this method fails more and more, because it's like, we call it fat tail. As much as the tail gets fatter and fatter, this method fails more and more. But then you can see that anyway, it's really good approximation. The dashed line is our extra approximations we did to have analytical result. Up to some point it's working well, but then you see that at some point start failing. And none of these methods, they tell us anything after the collision. So this is just, you can see it numerically. Then we showed that the acceleration as a function of this position of the kink. We showed the result for simulation. For the theory 2 is the one without extra approximation. Then you can see that they perfectly match. And our extra approximation slightly deviates from the simulation result, but still is not that bad. Okay, so I think the most interesting result, besides all the subtleties that we had to deal with, because when you have double long range tail, it's much more complicated to solve the system, and then it's not just simply using the method directly. So we needed to adjust the method. The interesting result for us was this not appearing the buoyant formation. So it just simply radiating away. So, okay, this was, I'm sorry I talked more than enough, but if you have any question, I would be more than happy to answer.
Qualquer coisa pode escrever as perguntas no chat, ok, pessoal?
Se alguém quiser falar em português, por mim tranquilo, só não tinha tempo de preparar em português a apresentação.
Hi, Azadeh, are you hearing me?
Hi, João.
It's really good to see you here. Thank you so much for your presentation. And thank you for the interesting talk. I would like to ask some questions. First, I would like to ask about I'd like that you say a little bit about the difficulty that you face to do this kind of simulation numerically, and also the approximations.
You're talking about the long range, right? I mean,
yes.
You talk about it can work. Okay. Mm-hmm.
And also, I would like to, if you could give some more details about that point that you talk about the interaction between the two solutions, or the collision between Kink and anti-Kink. If you are considering, for instance, that the two solutions, they have the same normal modes, or if you work it with solutions with different modes. And also, I think that one thing interesting would be, if maybe you were thinking about it too, but it would be to think about the applications that you can do with this kind of collisions. For instance, you have several scenarios with different kinds of physical behaviors, and maybe if you apply this collision or even that approach that you did with the normal mode, the excitation of the solution in a context, the context will constrain the free parameters that you have for the normal modes, for instance, and then maybe you can restrict yourself to one specific scenario of collision with an application.
Okay. So you asked all questions?
Yes.
Okay. So let's remember one by one. So you asked about the numerical difficulties. Actually, for both works, they were not easy numerically. There were a lot of problems appearing, and we needed to solve. For the first work was much lengthier. So with these collision scenarios that you're talking about, it's much more computer consuming. Okay, I mean, with these whole things, even like when we submitted the paper, the first one, referee asked some stuff that took us like almost 3 months to do all those simulations the referee asked to be able to answer the questions. So, but the second one is not as lengthy as the other one. The problem mostly was how to implement the method analytically and numerically, because there were a lot of subtle points here. Because, like for the simulation, this minimization that you need to do, and this with this heavy side form, because you need to. Okay, I'm not going through this why we use this, because it's really easy to show that this doesn't have the effect of that radiation, that extra pressure that appears to create repulsion. So this was the best method people came up with. It's not our idea. So then, okay, imposing this numerically, doing the list, the minimization and finding the result was not that trivial, but mostly we spent time to do the analytical part, which was the point is, people did, actually, it is a paper from last year in PRL, that people did with a class of models with one side long range, one side exponential decay normal tail, okay? Then, and they used this Manton's method. Then we started using it, but then it was not behaving well. Mm-hmm. And then we got that, okay, there are some points that doesn't match for double long range. We need to, the force that I showed, that it gets A minus delta A. In their case, the delta A is really small value, just they simply ignore it, okay? But in our case, it gets the approximations you're doing. You should be really careful, because the effect of delta A is comparable with A. Then this whole approximation, it took us a long time. I mean, long time, a few months, then to resolve these whole problems. But the numerical part, mostly, okay, my PhD student knows much more than me, so he's implementing numerically and just aware of the methods he's using, but I didn't do the simulation. So I don't know how technical you want to know.
No, okay, I'm pretty sure that is a large amount of work to do these graphics, and a couple of hours or maybe days to turn each one of them, probably.
Yeah, the result in the second work, actually, the result of the numerical calculation, it doesn't take long time to run. The problem was how to implement the system. It was more because there were there are appearing this last year, a lot of papers to suggest that what can we do to solve the problem, okay? Mm-hmm. So we needed to really read to see for each thing what people think, what didn't work, and even now see in our system, does it work? So it was really non-trivial, this part. Then I forgot the other questions. Let me see.
Sorry, I asked everything in once, so it's my fault. It's not your fault.
You asked about.
But the second question was about two different kinds of normal modes. If you consider kink and anti-kink with two different modes, because it seems that you consider the same perturbation for each one. Is that correct? Or
yeah, for the first work, yeah. Mm-hmm. For the first work, because okay, this is what we did. We had a lot of a few parameters to control these normal modes. Then there are a lot of questions here. If you have more than one normal mode besides the translational mode, the zero mode, if you have, there can appear a lot of strange things. I mean, even the resonance window can close. I mean, it doesn't appear. Okay, it can happen. We wanted really to isolate the quasi-normal mode effect, because we wanted to see what is expected for normal mode, what is expected in literature. Then if you make that normal mode to quasi-normal mode, what is the effect? So we wanted really to isolate this effect, okay? And, okay, if you have two kinks in the system, the system has the parity symmetry, so it would be really strange. You provoke one of the kink to be in one normal mode and the other one in another normal mode. I mean, why should it happen? This is, I don't know exactly how to justify this, okay? I mean, we are studying the same system, the kink and anti-kink appearing in the system, and if they interact, what happens? But if you want to put, okay, you could put different solitons or different modes to be excited. Different solitons, it would be really strange, because how you want to create a system that creates two different solitons? It's a little bit strange. But if you want to excite different modes, then somehow the symmetry of the system, I don't think lets it happen. If you want to do it, probably you need to, break some symmetries of the system, I guess. Did I answer your question?
Yes. I thought about it because some years ago, I guess in the end of 90s or 2000 or something like this, there was a series of papers talking about Hermitian systems where people worked with different kinds of oscillations or harmonic oscillators with different modes. So you could have, they call it anisotropic oscillators, that kind of application. But it was interesting because there was some non-trivial effects that happens the effects, they depend on what kind of Hamiltonian you were choosing.
Exactly, this is the point. I think you should break the symmetry of the harmonic oscillator at the level of Lagrangian. So explicitly, you should break the symmetry. I think, to have unharmonic modes. I mean, to create. So in this case, I guess you should probably break at least parity, I would expect.
Yeah, probably.
Yeah, I guess. Okay. No, interesting. I would like to see.
It was interesting. This series of papers were very interesting. They were made from people. I don't remember where was the place. I guess it was from MIT or something. It was the group of Bender. I don't remember the first name, but it was a series of physical review letters talking about this kind of phenomena with anisotropic oscillators. So maybe it's interesting to see if you can adapt this to kink and anti-kink collision.
Yeah, actually, it's a nice question. Yeah, I would like to see one of those papers.
I can send some of them. There's no problem. And the third question was about the applications. If you could constrain these parameters that you have, or the scenarios of collisions with application, with a specific application. For instance, you talked in the first part about the polyacetylene. If you could make any constraint of the collision, or about the perturbation, or even about the perturbation with this kind of application.
I agree. It would be really nice to look at it. No, at this point, because for us, it's like a work in the last 1-2 years. So still we are working on the fundamental concepts. I mean, the ideas behind. But I would love to see how they have to see the applications. I know that people always mention some applications, but still I didn't really focus on that. But I guess there would be a lot of nice applications, like in, I don't know, like the domain walls or kinks appearing in ferromagnet materials, or, I mean, in different contexts, it could appear. Yes. Yeah, I would like to see that too. But unfortunately, I don't know much.
Okay, thank you. Thank you so much again, Azadeh. It's really nice to see you. Hope that everything is okay there with you. And hope we can see ourselves together soon.
I really hope so, physically. I mean,
yeah.
Okay. Thank you, Joe.
Thank you.
So, any other question?
Azadeh, eu tenho, mas eu posso falar em português?
Claro! Oi, Rúmulo.
Oi, Azadeh, tudo bem? Como é bom vê-lo novamente. Olha, eu me interesso muito por fenomenologia, né? Aplicação, né? E eu fiquei muito interessado na motivação do poliacetileno. A minha pergunta é, porque eu estava meio perdido no seminário, que eu acordei na hora do seminário, sabe?
Okay.
A minha pergunta é, o φ(x) é o que mesmo? É o campo elétrico, é? Era o quê?
Não, isso é só o campo que você está definindo por o que é displacement, deslocamento, ok? O campo φ de x é deslocamento que está olhando na posições diferentes, ok?
O deslocamento das moléculas do poliacetileno, é isso?
Sim, exato, de elétron. Perto de, está oscilando perto de o electron site, o ponto que tem o átomo, não é?
Sim, tem um átomo, aí tem, assim, né? Tem as moléculas, né? Na verdade, tem as moléculas, né? E os elétrons estão, como é que chama? Externo à molécula, não é isso? Aí
E tudo move junto, ok? Então, o que está acontecendo imagina, tem o atom site, ok? Então, com temperatura não zero, ou o efeito de Casimir, qualquer coisa de vácuo. Imagina, em forma normal, o que você esperava é só o átomo começar a oscilar no mesmo lugar, não é? Só oscilando. Mas o que está acontecendo? O átomo vai mover para a direita ou esquerda, ok? E só um pouco deslocando e depois oscilando. Então, o que é importante para definir aquele campo é região que está conectando essas duas regiões com moléculas que estão indo para a direita e oscilando ou indo para a esquerda e oscilando. E essa transição cria um domain wall, mas não importa, pode chamar Kink aqui, em uma dimensão. Então, esse deslocamento está definindo uma coisa que conecta um vácuo para outro vácuo, no sentido de um defeito topológico.
Então, só resumindo, para ver se eu entendi. O φ de x, então, é o deslocamento.
Sim.
É a posição do elétron, né, ao redor da molécula, não é isso?
Não importa, de molécula, tudo junto estão movendo.
Conjunto. Entendi agora.
Deslocamento daquele conjunto.
Entendi. Ou ele está no vácuo mais baixo ou no outro mais alto. Agora eu entendi. Obrigado, Azadeh. Foi um prazer revê-la, viu?
Prazer para mim também.
Acabou minha participação, João.
Obrigada. Então, mais perguntas?
Eu tenho uma pergunta.
Ok. Oi, Messias.
Boa tarde, professora. Tudo bem? É um prazer lhe vê-la, mesmo que virtualmente. Uma ótima apresentação.
Obrigada.
Eu tenho algumas dúvidas para tirar com a senhora.
Ok.
Eu estou mais acostumado com o termo modos quase normais no contexto de buracos negros, certo? Ondas gravitacionais mesmo.
Uhum.
Certo? Então, quando visualizamos o espectro da onda gravitacional, antes da colisão dos objetos compactos,
Sim.
Vamos ter antes da colisão e logo próximo à colisão, ou durante a colisão, vamos ter um pico e depois começa a decair.
Ok.
E lá no final, vamos ter a questão das oscilações gravitacionais, que no contexto de gravitação é onde vive os modos quase normais. Então, minha primeira pergunta é, nesse contexto que está simulando em matéria condensada, né, mais aplicação,
Para o Kink, pode ser.
Um comparativo.
Uhum.
Então, a minha pergunta primeiro seria, existe um comportamento nesse espectro similar a o ring-down, no caso do comportamento da onda gravitacional?
Você quer comparar o resultado ou o conceito? O conceito é muito parecido. O conceito é parecido, porque, por exemplo, para ondas gravitacionais, se você olhar modos quase normais para campo gravitacional, os modos, o que acontece? Por que é quase normal? Porque é o número complexo, aquele modo. Porque
é um sistema dissipativo, né?
Exato, e está espalhando para até infinito, porque o sistema não está fechado, não é? Está decaindo.
Uhum.
Você tem um lado buraco negro, então qualquer coisa entrar não sai, e o outro lado tem até o infinito pode espalhar, ok? Então, esse sistema é dissipativo e nesse sentido é a mesma coisa aqui. Porque eu coloquei duas barreiras, então a energia está penetrando daquela barreira e a gente tem só outgoing boundary condition, ok? Que no caso eu não sei muito sobre modos quase normais em buraco negro, mas eu acho que é ingoing, é só ingoing, não é?
Isso.
Mas não importa, só existe um lado, não tem volta. Então, só tem transmissão, aquele de voltar parcialmente, isso não existe. Então, conceitualmente é bem parecido, mas o resultado eu acho que depende de coisas que você está olhando. Eu acho que não é tão comparável, só a energia está saindo do sistema, então os efeitos ficam parecidos, mas acho que não mais do que isso, para comparar.
Certo, entendi. Outra questão os modos quase normais, a parte imaginária é sempre negativa?
Não, pode ser positivo. É só que um deles vai ser instável, não é?
Ok, certo.
Um deles vai só exponencialmente crescendo, outro exponencialmente diminuindo. O que é exponencialmente diminuindo é o que é estável no sentido de físico, não é?
Sim.
Se aumentar, fica dominando a energia do mundo, não é? Então, então só um sinal é relevante fisicamente.
Certo. Outra questão é a questão, não sei se nos seus resultados aparece cada modo quase normais, dependendo apenas dos parâmetros do Kink, ou então do sistema.
Do sistema, exato. Que é parâmetro de Kink.
Só dos parâmetros que caracterizam o sistema.
Exato. exato. O parâmetro que está definindo que tipo de kink está aparecendo, com que geometria, ok? O que é mais importante para a gente. A gente não mexeu com os valores de fronteiras. A gente queria ficar com a mesma topologia, ok? Valores de...
porque no sentido gravitacional, o que se espera é que os modos quase normais não dependam do que ocasionou a colisão ou a perturbação do sistema, e apenas os parâmetros que caracterizam o sistema, no caso, os buracos negros. Tipo massa, carga e...
Exato.
Então nesse sentido também tem essa analogia, né?
Tem, exatamente. É boa observação. Exatamente.
E a questão, não sei se apareceu um N nos gráficos da senhora, vai crescendo ele naturalmente, é sem limite, esse valor de N?
Qual? Não entendi.
Os modos quase normais dependem de um parâmetro N lá, discretizado. Eu acho que está nos últimos slides da apresentação das...
De primeiro trabalho, não é? Porque foi sobre modos quase...
Não, aqui, ó.
Aqui?
Não, mas para onde?
Não, isso
mas é um N.
Deve ser, o que você está falando, deve ser aqui, em algum lugar. Aqui?
Então, esses ômega quadrado depende de um parâmetro discreto N. Talvez dependa. Eu estou falando, não sei se no caso da senhora isso acontece.
Não, aqui não, porque a gente tem só um modo normal
tá certo.
E a gente só mudando aquele modo, porque a gente não queria uma bagunça de modos diferentes.
No caso aqui seria o modo fundamental, o mais importante, né?
O modo que eu estou falando é excitações de campo de kink, ok? Então, a gente está olhando perturbações daquela solução. Vamos mostrar aqui. A gente está olhando aqui, abaixo da equação 4, a gente está perturbando a solução de kink e os modos têm relação com aquele ômega aparecendo aqui. Então, esses modos são modos daquela perturbação. Que o modo zero é só por causa de simetria, translational symmetry, ok? E abaixo disso fica um modo excitado, que todos eles são modos normais do sistema. Só que você tem que provocar, não é? Aquele modo. Você tem que dar energia para ir para o estado mais excitado daquele kink, ok? Então, porque a gente tem só o modo zero, que é irrelevante, só a gente queria garantir isso existe, porque tem a ver com simetria. E, além disso, tem só um outro modo normal. E agora, se esse modo fica quase normal, se tiver número complexo, se tiver decaimento, o que vai acontecer em excitações de kink e o que acontece na colisão.
Claro? Entendi, muito bom. Uma última pergunta, professora. Na questão de gravitacional, pelo menos, eu tenho dificuldade em ver como eu botaria uma possível violação de Lorentz. Mas nesse contexto que a senhora apresentou aqui, talvez seria bem mais fácil de implementar, né?
Se quiser quebrar a simetria de Lorentz, sim, é fácil.
Seria mais fácil, né?
Mais fácil.
Muito boa a apresentação. Obrigado, viu, pelas...
Obrigada, Messi. Foi bom ver você.
Tchau. Também.
Professora, boa tarde. Belíssimo trabalho.
Boa tarde. Obrigada.
Assim, eu sou meio leigo nessa parte de topologia, mas eu pesquiso um pouco sobre matéria condensada. Eu trabalho sobre o princípio da DFT. E a senhora falando agora com o Messias, me veio a seguinte dúvida. Porque quando a gente está trabalhando lá, quando a gente pega um cristal e a gente calcula os modos normais, que a gente chama os modos normais de vibrações, isso vai nos influenciar diretamente se o material ele pode ser sintetizado ou não, certo? Então, quando a senhora fala sobre esse modo normal, é o mesmo modo normal que a gente trabalha no contexto da matéria condensada, que a gente pode dizer que os modos normais vai nos trazer como resultado a possível sintetização do material ou não? É isso?
O modo normal aparece em muitos contextos. Isso é modos que está caracterizando cada sistema. E sistema pode ser clássico ou quântico. Então, nesse caso que você está dizendo, é uma aplicação. Então, o conceito de modos normais é um conceito que já em mecânica clássica, já vocês viram, tipo, se tiver mola, não é? Uma mola.
É uma corda vibrando também, né? Uma corda vibrando.
Agora você pode olhar modos normais do sistema. Então, o que você está dizendo pode aparecer em muitos casos. Só com esses modos normais, você está caracterizando aquele sistema. Então, não é para uma coisa específica. Depende do que está estudando. Mas
esse modo normal que a senhora está falando, é isso que eu acho que não ficou bem claro. Esse modo normal que a senhora está falando é o mesmo modo normal que aparece lá para quando a gente está fazendo os cálculos quânticos de um cristal, de uma rede cristalina?
Mesmo não faz sentido o que eu estava dizendo. É modo normal.
Entendi agora.
Normais de perturbação de Kink. Ok? Então, você pode olhar modos normais de quê? Ok? Então, você está olhando aqueles materiais.
Entendi.
Eu estou olhando modos normais de outro tipo de coisa. Ok? Mas ideia
porque
atrás...
o conceito de modos normais, né? O conceito de modos normais, eles são, vamos dizer assim, um campo muito vasto, né? Aí, não, será que é o mesmo que a gente, quando está trabalhando, usando a aplicação da FT, é o mesmo modo que aparece? Porque tem hora que possa ser semelhante, né?
Sim, conceitualmente é a mesma coisa. Só que, modos normais de que você está estudando? Em que contexto? Então, coisa atrás, coisa mais profunda, é a mesma coisa, ok? Mas, depois vai ser dependendo do sistema que você está estudando. Mais perguntas?
Muito bom, professora.
Obrigada.
Não, tranquilo, muito boa. Eu acho que a apresentação da senhora, ela tirou, pelo menos no meu ponto de vista, sancionou muitas questões de dúvida que eu tinha, certo? Muito obrigado.
Obrigada. Mais perguntas?
Uma questão, pessoal. Eu ia fazer uma pergunta, mas era endereçada aos estudantes também. Qual foi a linguagem de programação que vocês usaram? Como é que vocês implementaram isso?
Não entendi, desculpa.
Qual a linguagem de programação que vocês usaram? Como é que vocês implementaram isso?
Foi mistura de muitas coisas. Usamos mistura de Python com matemática, com C++, e acho que foi esses três. Eu não fiz, foi João que fez, mas eu sei, pela conversa com ele, percebi que fez em os três. Depende porque a gente fez, para cada coisa fez simulação. Então, às vezes foi mais fácil fazer em Python, às vezes foi mais fácil em programar em matemática ou em C++. Mas sei que ele usou Só esses 3.
Só não.
Só. Não sei, eu respondi a sua pergunta?
Sim, sim.
Ok, perfeito.
Mais alguma questão, pessoal? Eu acho que vamos agradecer.
Eu tenho uma pergunta.
Ok. Oh, oi, Francisco. Tudo bem?
Tudo bem, querida? Desculpa aí. Só agora. Eu estava tentando... eu estava ouvindo as perguntas aí para ver se eu conseguia capturar o que foi apresentado, né? Porque eu cheguei já no fim.
Ok.
E você passou alguns slides para trás, aí eu pude capturar um pouco do que foi falado.
Ok.
E também, baseado no seu resumo, eu consigo imaginar mais ou menos o que foi apresentado. Claro que teria sido melhor ter visto todo o seminário. E pelo que eu vi, pelo que estão falando aí, foi um sucesso. Meus parabéns em antecipação.
Obrigada.
A minha dúvida é só uma coisa. Vocês têm levado em conta, nesses modelos, o problema de integrabilidade? Quem sabe, por exemplo, colisões de objetos, né, kinks, que vêm de teoria de Sine-Gordon, eles têm um tipo de interação totalmente diferente, por exemplo, de modelo.
Exato. Que não é tão interessante, porque é integrável. Exato.
Então, eu acredito que vocês, quando estão estudando coisas que têm interação, não pode ter integrabilidade, é isso? Se tem integrabilidade, não tem interação, é isso ou não?
Só não é interessante. O ponto é, por exemplo, no Sine-Gordon, que é sistema integrável, se fazer colisão, eles simplesmente passam. Um passa o outro. Então, nada interessante acontece, porque é integrável. Então, o que fica mais interessante, e na literatura tem mais sobre colisão, é para sistemas não integráveis, porque depois de colisão é caótico. Então, você não sabe o que vai acontecer. Então, tem que... essa estrutura fractal, ou aquela janela de ressonância, essas coisas, tudo aparece só para sistemas não integráveis. Mas se tiver integráveis, simplesmente eles passam sem perceber nada. Então, por causa disso, não vi muitos trabalhos fazendo interação entre defeitos de sistemas integráveis.
Legal, bacana isso. E outra coisa, essa interação, você leva em conta curto alcance, longo alcance, ou só quando ele toca um no outro?
Alcance é o quê?
A interação que você leva em conta é só quando eles entram em contato? É só força de contato? Ou tem interação de longa distância também?
Não, a maior parte de coisas no início estão em longa distância. E depois, porque estamos tratando os campos, então não precisam ficar muito próximo. Por exemplo, no caso de kinks com long range tail, eles são muito interativos. Então, o que acontece, até é mais fácil tratar sistema se eles ficarem longe. Ainda eles vão interagir muito. A força entre eles é grande, mas se colocar muito próximo, até não sabemos como tratar sistema. Então, porque interação eles ficam tão distorcidos que não pode simplesmente colocar um kink mais um anti-kink agora saber quem é quem. Okay? Mas depois de colisão, agora, se começar bem para a parte numérico, porque depois de colisão não existe nada analítico. Agora, se fazer... eu fiquei perdida. O que eu queria dizer... esqueci.
É sobre interação de longa distância. O long tail... Eles, por ter um long tail, eles conseguem interagir mesmo a longa distância, e sim, você quer o regime melhor de tratar analiticamente, porque depois disso...
Eu estava dizendo isso, que para começar, por exemplo, para programar, no começo tem que colocar eles em longa distância, porque a gente não sabe como colocar muito próximo.
Sim.
Depois que o quê? Agora, em colisão, o que acontece, o final, o que vai acontecer, o programa vai dar. Pode ver o resultado. Então, eles ficam muito próximos. Só que, para começar ou fazer coisa analítica, isso é muito difícil. Realmente, não conheço nenhum trabalho fazendo isso analiticamente.
Sim, seguramente é muito difícil. Obrigado. Bom trabalho.
Nada.
Belíssimo trabalho, isso aí.
Obrigada.
Esperamos encontrar em breve.
Eu espero que sim.
Ou online ou fisicamente. Fisicamente é uma proposta a longo prazo ainda, infelizmente.
Eu acho que sim, infelizmente.
Obrigado.
Obrigada a você. Então, mais perguntas?
Bom, acho que a gente encerrou as perguntas, né?
Uhum.
Então, gostaria de agradecer novamente a Azadeh, em nome do Douglas e de toda a UAF aí pela sua participação nos nossos seminários aqui. É um prazer te ver novamente. E também queria só comentar aqui rapidamente que a gente teve uma boa audiência aqui dos nossos estudantes. Tivemos a presença também do Anderson, que é nosso colega lá da Rural, coordenador do programa de pós-graduação da Rural de Pernambuco. Então, foi realmente muito legal, muito interessante o seu seminário, parabéns.
Obrigada.
Espero que logo a gente se veja novamente.
Espero que sim, e sempre é prazer ver vocês e apresentar o meu trabalho. Obrigada.
Obrigado, Azadeh.
Obrigada.
Pela apresentação, parabéns pelo trabalho.
Obrigada.